Okay, this is a case where a spindly two-layer linear network whips any neural network with a fully connected input layer. The referees didn't like the term whips. We had to replace it by decisively outperforms, which is kind of boring, but that's it. Joint work with Wojciech, Kotłowski, and Ehsan. Okay, here is our paradigmic sparse linear problem. You have a matrix, the rows are the instances, and one of the features is the target. So here's the fourth feature, third example, and the -1 is the label, right? So I'm picking out with a linear vector, a linear unit weight vector, one of the features. Here's an example, square loss, additive update, just subtracts the gradient of the square loss, multiplicative update puts those in the exponent. Okay, so assume you have a 128-dimensional Hadamard matrix. The matrix are orthogonal plus -1. Then after seeing 64 examples, half of them, all the weights, the 128 weights are in blue, and the good weight is about half, and all the other weights still hang around. The average square loss in red goes down linearly, and it's still a half after seeing half of the examples. The size of the problem is log n, because you have n features, or d features, log d. The multiplicative update learns essentially after log dimension many examples. Its average loss goes down exponentially fast, and the good weight is picked up exponentially fast. So here's again Hadamard. The conjecture was, together with Mikhail Derezinski, that the linear lower bound, this lower bound here, still holds for any GD-trained neural network. Okay, that's not true. Here's a spindly network. If you train it with gradient descent, it cracks the Hadamard problem. It's the linear neuron, except the edges are doubled. Okay, and in the continuous case, this one simulates the unnormalized exponentiated gradient algorithm exactly. In the discretized case, in the finite step case, it does it approximately, but good enough. You can prove the same work at bounds. The square reparameterization trick was introduced to me by Gunnar Sakar and Sreiber et al. They introduced it in the matrix context, but it was known to the game theorists since the 70s because the multiplicative update is related to the replicator dynamics of evolutionary game theory. And there they try to simulate that with gradient descent. Okay, what we show here is that the linear lower bound still holds if the neural network has a complete input layer. So conjecture falsified, conjecture fixed. If you have a complete input layer, then you still have the lower bound. So there was previous lower bounds, very similar ones, but key differences as well. They are SVD based. They showed the same linear lower bound, even if you expand the instances with an arbitrary phi map. However, those lower bounds only hold for linear neuron. They can't go below 2 layers, and they restricted to square loss. Here, we don't have the expansion, but we show the lower bound holds for a fixed function. It's kind of surprising. And for very, very general losses. The key trick is, as soon as you have a complete input layer, you have rotation invariance, and that is a certain liability. And this is a really nice punchline that should be interesting. Okay, here it is. Neural network depiction. Here's the input layer in red. Any node that gets any input has to get all inputs. These nodes are trained with gradient descent. All the red weights are trained with gradient descent. Rotation invariantly initialized here. Over here, it doesn't really matter what you do. Any initialization, any transfer function, anywhere. For simplicity, single output node. We want things to be differentiable for simplicity. Okay, so it's a very general thing, and we're going to have very general losses. Here are the losses. This is the output, the y hat of the whole neural network. The loss at the end, if you have this property that label minus and +1, the loss on the average is bounded away from 0, then the lower bounds apply. C, of course, enters into the bound. Now, we, in this talk, restrict ourselves to convex losses. In that case, for the purpose of lower bounds, by Jensen, you can restrict yourself to deterministic algorithm. For simplicity, let's just take square loss where C is 1. But it holds more generally. Key thing is rotation invariance, right? Rotation invariance, what is that? You have a predictor, which is this mapping. It relies on the examples, right? The past examples, the training examples, let's say half of the matrix. And then this is a test instance. And that's the prediction. Good. Now, if you have the property that if you rotate the training instances and the test instance, nothing changes, then we say it's rotation invariant. Okay, so we rotate and counter-rotate. Now, of course, gradient descent has that property if the input layer is complete, because you rely on complete dot products, and all the derivatives of the weights in the bottom layer are a constant times an instance. And if the instances rotate, the weights counter-rotate and nothing changes. So the key is, again, any input node that receives an input feature must receive all. Now, this rotation invariance is not something just related to gradient descent. If you have complete input layers, then Newton's method, Adagrad, Adam, they all rotation invariant. We give a list at the end. Okay, good. Now, interlude. The multiplicative updates are decidedly not rotation invariant. Why? They access individual features. You see, the factor relies on the individual feature. Okay, so that's the exponentiated gradient algorithm unnormalized. This is the spindly network which simulates it. I did it in terms of squares because it's the combined weight. And this factor here, if you square it, you get 1 minus eta gradient, which simulates, which approximates, of course, the exponential. So you immediately see the relationship. So these are not rotation invariant because they access individual features. The rank of the combined weight space grows exponentially fast. Okay, here is the simplest case. Hadamard, constant target, the first column. Well, that's a little bit too easy. So what you need to introduce is some random sign flips. So, for instance, an instance might be multiplied by -1. So then you flip all the instance, all the features of the instance, and you flip the label, right? And you randomly flip all the instances. If you do this, you end up with a new problem. And now you rotate that problem. You make up a rotation matrix that incorporates those random sign flips. This is the original problem with the sign flips, and then this is the rotated one. But the rotated one rotates everything to the identity. So in other words, and the predictions of the rotation invariant algorithm on this and this have to be the same. So in other words, there's no difference. The labels don't show up. There's no information about the past labels in the instances. And if you fix the past labels, which were random, they had no information. The future labels are also random. They have no information. So the best thing you can do is on the unseen d minus k instances predict 0. So, and the average square loss then becomes d minus k over d, which is this familiar lower bound. So there's no way to fix this. As soon as you have rotation invariance, the algorithm is totally lost on all the unseen instances. And you have to do the sign flip, of course. Then the algorithm is totally lost on the unseen instances. Okay. The lower bound holds even for rotation invariant initializations. There's versions when you have 0, 1 features instead of +/-1 features. And of course, the more general losses. There's also cases where these lower bounds hold when the instances are Gaussian. They're slightly weaker, so far only for square loss. We don't know how to do it for more general losses in the Gaussian case. We also conjecture that these lower bounds hold when you have random ±1 instances. Trivial to check experimentally, but we don't have a proof yet. What's the big picture? We have a notion of rotation invariance that corresponds to the weights being a linear combination of the examples. Then Hadamard, because of orthogonality, is a hard case. And then you get the lower bound. There's a related notion of rotation invariance for multiplicative updates. It's a two-sided notion now. You multiply in the left and the right with an orthogonal matrix and nothing changes. There's a notion of linear combinations. This is more general. I don't know what corresponds to the Hadamard problem and the lower bound. Partial work done with Wojciech, Kotłowski, and Chu Sheng. We showed that if you have a complete input layer, then you cannot learn a single target because you have rotation invariance. Of course, a single target is trivial to learn with a phi map. You just take the instances and map them to the target, then you have nothing to learn. But we conjecture that if you want to learn all target and be good on all target on the average, then the lower bound, the linear lower bound, is robust even for arbitrary phi maps. Okay, that's a beautiful open problem. Here's the rotation invariance of Newton's, Adam, you can look at those slides yourself. Voka, Suri, Warmuth, Foster, Warmuth, various linear regression algorithms, they're all rotation invariant. Thank you very much.